In this video, we're going to extend our op-amp analysis to include inductors and capacitors by talking about impedance in op-amp circuits, which will let us use op-amps to build interesting filters. Now, this process of adding inductors and capacitors to our op-amp circuits is not only cool because of the filtering properties that we can generate, but it's also cool because it lets us tie into one of the main tricks from E79, which is that we can treat inductors and capacitors exactly the same way as we treat resistors, as long as we use frequency domain analysis and only deal with input sine waves. So we're just going to take our existing op-amp analysis and sprinkle them with a few E79 techniques in this video. We'll use this circuit as our first example. Looking at it, we can see that it looks kind of like an inverting amplifier, and we already know the gain of an inverting amplifier. So if we substitute the impedance values of R and C in place of the Ri and Rf equations from the gain we derived earlier, then we find the output voltage is given by Vin over RCS. You may remember that a factor of 1 over S corresponds to integrating the input signal. So this device performs integration, and in fact the circuit is called an integrator. That's cool. The fact you could use this to make an integral was actually really important to early computing. When you wanted to solve a tricky differential equation, what you would do is build a whole bunch of different integrator circuits like this one, and stick them together in order to form a differential solver. Those were called difference engines. Now, you need to actually be a bit careful with the input signal you give this circuit, or you're going to get a boring result. If you apply any DC voltage, the output is going to integrate it forever, which means this thing rails out quickly unless there's a zero-centered AC signal on Vn. I'd like you to pause the video and take a crack at finding the behavior of this circuit based on the techniques we employed last slide. You can probably even guess the circuit's name from your answer, so go ahead. Alright. We go through the same steps here. We notice this looks like an inverting amplifier, then we substitute impedance values for RF and RI, and finally do a bit of algebra to find out that Vout is equal to Vin times RCS. Multiplying by S corresponds to a derivative, so this is called a differentiator. I'm not going to do the math for you, but in this slide I've included pictures of high and low pass filters. The trick is that RI and RF for these look like series or parallel combinations of elements, and that's still fine. You can find the impedance of the series or parallel combination, like this one here, and then analyze these op-amps in exactly the same way. So when I give E80 students low and high pass filters like I did in the last slide, they mostly run off and make bandpass filters by combining a low pass in series with a high pass. And that actually works pretty well. Op-amps are really good at separating out the impedances of the low pass and the high pass filter, so they can be stuck together like that. But it turns out you can actually make an even better bandpass than that using something called a Sallen-Key filter, which I've shown here. So for instance, you can get a fourth order bandpass filter using only one op-amp if you use this topology. Now, this might save you some soldering and debugging, but it might also be too tricky to really implement. Feel it out when the project comes around. So in summary, you can use inductors and capacitors in an op-amp circuit in order to make filters. And you can analyze those filters by replacing the resistor values with the impedances of capacitors and inductors. And finally, Sallen-Key filters might save you some components in the project.